Hello everyone. In this video, we are going to check the shear capacity in column and how much transverse reinforcement we have to provide in the column. This is as per IS 13920. So we have already calculated the forces in the multi-story frame, and we were designing for the column this, which is DA. So same, this column will be checked for the shear. If you see in the plan, the position of the column is here. Okay, so this is the elevation and this is the plan. So if you refer the previous videos, you will understand that we are designing this whole multi-story building step by step. Now, for the shear capacity of column, how much reinforcement we have provided in the column. So in the last video, I have given the link. We have calculated the reinforcement required for the column. So we have provided the minimum reinforcement and we have checked for the biaxial bending. So 0.8% we have provided. So I'm going to divide by 2, 0.4%. So this I have provided because I'm assuming that 50% of the steel is provided for the tension, okay, and 50% for the compression. Okay, that's why I'm dividing by 2, and for this amount of reinforcement I'm going to calculate the shear capacity. So if you refer table 19 of IS 456/2000, so you will get the value of tau c, that is the shear capacity. So you might have also referred many times for the beam. So referring this table for the 0.4%, so the value will be in the table. If you see, there is value for 0.25% of reinforcement, which is 0.36 tau c value, and for 0.5% the value is 0.49. So interpolating this between these two values, it will be like 0.36 plus 0.49 minus 0.36 by 0.5 minus 0.25 into 0.4 minus 0.25, right? We are calculating for 0.4. So this value is 0.439. So this Newton per mm square. Now, if you refer clause number 40.2.2, so this table we usually use for beam. So in order to calculate the shear capacity for an axial member like column, we have to multiply that with a factor delta, which is 1 plus 3 pu by ag by fck. So that will be plus 1 plus 3 into what is the axial force that is coming to the structure. So 153.07, this value is in kilonewton into 10 to the 3. So this, if you are referring the load calculation or the previous video where we have calculated the axial force coming to this column DA, okay, in this multi-frame, if you refer that video, you will come to know how this value has come after the analysis of, like, we have done gravity load analysis and the lateral load analysis. From there we have calculated this axial force coming to the column. So 3 into P by gross area. So column size we have taken 400 cross 500. This is our size of the column we have assumed. So 400 into 500 into FCK is 25. So this value is 1.09. So the shear capacity of the column is, we have to multiply delta, that means 1.09, into the value that we have got from the table 19, 0.439. So the capacity is 0.479 Newton per mm square or megapascal. Okay. Next. So this is shear stress capacity. This is stress, we have to calculate the shear force capacity. So shear force will be, that means shear stress. So if VC I'm writing in x direction, y direction, because we have two axes. So if this is the column, this is 500 and this is 400 we have considered. So this is x-axis and this is our y-axis. Both axes will have different shear force capacity. So this is tau c into area we have to multiply, because this is shear stress into area. Okay, so we are going to multiply tau c into area. Okay. Now area will be, so for we have to calculate the effective depth. So if it is in x direction, depth is, if this is x direction, 400 is the depth minus d dash. Okay, so if d dash, if you refer the previous video, we have also already calculated. Clear cover 40 plus 8 is our tie or tie bar plus longitudinal bar by 2, 16 by 2, which is 56 mm. So 400 minus 56, it is 344 mm. Similarly, the effective depth in y is 500 minus 56, which is 444 mm. So for this, the tau c is 0.479. I'll multiply with the width 500 into depth 344. So this is coming 82.4 kilonewton. Okay, by 1000 if you do, you'll get in kilonewton. Similarly, 0.479 into here is 400 width and 444 is our depth. Okay, so here the value is 85 kilonewton. So this is our shear force capacity from the shear stress capacity we have calculated. Now this is the capacity, that means this much force it can take, the column can take as per the reinforcement provided. Now we are going to find out what is the shear force coming to the structure, right? Whether it exceeds the shear capacity or not, we have to calculate. So now calculating the shear force. So shear force, as per the structural analysis we have done, we have found that the shear force due to gravity load, we didn't get any shear force. So this, you can refer the video where we have analyzed the frame using substitute frame method. Then for the earthquake in x direction, we have analyzed the frame. So when we have analyzed, if this is the dA column, we have calculated the force, right? Here we have calculated the force. The shear force was 30.85 kilonewton. So this I'm going to multiply 1.2, because this is the factor that we are taking for the analysis. Okay. So now adding to this, we are getting 37.02 kilonewton. Okay. Because 1.2 dead load plus live load plus earthquake X. For this load combination, we have analyzed all our structure. So same load combination I am considering. Okay. But in real, we have to consider all the load combinations. So for this kilonewton, this is as per the structural analysis. And then second, we have to consider also due to shear force due to plastic hinge formation. At beam ends. Okay. So for this, so I'll just take this as Vs. Okay, what is the shear force coming to the structure? So 1.4 into, for this, we have to take the moment capacity, okay, of the beam. So in sagging as well as hogging, 144.6. So you can refer the video, maximum of MS and MH. That is moment due to sagging and moment due to hogging. So 144.6 by 3. 3 is the length of the column. Okay. So this comes 67.48 kilonewton. So if you take, this is the shear force coming on the structure. And what is our shear capacity? It is 85 kilonewton. That means we don't need to provide more shear link. We have to just provide the minimum shear links. Okay. As it is less than shear capacity. That means the force that is coming on the structure is less than a capacity of. So we have to provide minimum shear links. Otherwise, so this I'll take, else let me just tell you, if it would have come more, then the shear spacing, the tie links that we should have provided, the spacing would have been, for example, if I'm using 2-legged of 8 dia bar, so into 0.85, sorry, 0.87 Fy by the difference between the shear force capacity and shear force coming on the structure. Okay, so you have to calculate this and you will get the spacing. But for in our case, if we are providing the minimum shear links, so we have, if we refer clause 7.4.2 of IS 13920, so the spacing should be maximum of 300 mm or half of your minimum lateral dimension, which is 200 mm. So I am going to provide 2-legged 8 mm dia at the rate of 200 mm center to center. So note, this provision is for nominal links. That means we are going to provide this at in columns at mid height. Okay. Then next we have to calculate for confining links. That means near the joints, how much we need to provide. So if you refer clause 8.1 of IS 13920, so in this clause 8.1, in the first bit A, the spacing has given. So length spacing, that means the tie bar spacing, when you're providing, it should not be greater than 1/4 of your least lateral dimension, which is 100 mm. It should not be greater than 6 into the dia, longitudinal dia bar. So we are using 16 dia bar, right? So if this is our column, this is our 500 dimension, this is 400 dimension. So previous video we have calculated the longitudinal reinforcement required, which we have seen that 8. So this was 8 numbers of 16 dia bars, right? Now we are calculating this lengths. Okay, this we are calculating. So 16 into this 6 into 16 dia, 96 mm, and it should not be greater than 100 mm. So if you see minimum, it should be, so spacing should be less than 96 mm. And confining length, so this is in bit B, confining length on either side of the joint, that means beam column joint, on either side of joint. So what is the length? It should be maximum, or if you see, it is written not less than larger dimension, that is 500, larger 500, 4 and 500, 1/6 of the length of the column, which is 500, or should not be less than 450 mm. Okay, so that means 500 mm. Maximum of these values are 500 mm. So if this is the column, so here beams are there. Okay, this is our DA column. So we have provided 3 longitudinal bars. Now this confining links should be provided from joint to 500 mm length. That means here. These are the confining links. Okay, these are the confining links. And then you have the normal nominal links. Okay, this you have to provide the nominal links. So these are the nominal links. And the green colors I have shown, these are the nominal confining links. Okay, this links for confining nominal link, we are providing 8 mm dia at the rate 200 mm center to center. And for the confining links, we are going to calculate, okay, we are going to calculate ASH. So if you refer the clause, for the rectangular column, it has given the formula, it should be maximum of 0.18 SVH FCK Fy Ag by Ak minus 1, and there is another formula where you will get less value of spacing, so I am going to more spacing value, so I am going to take this greater one value. So I am using two-legged, if I am using two-legged pi by 4 8 square, two-legged 8 dia link 0.18 SV into your H is 500 minus 40 minus 40, clear cover, because your stirrups are there all side. So if this is your column, so this is your stirrup, right? So you have to calculate this length H. So 500 minus 40 minus 40, you are going to get 420 into FCK is 25, Fy is 415. Your gross area is 400 of column, 400 into 500 by AK will be 420, like you calculate 500 minus 400. Same, you have to also calculate in the other direction, so it will be 320, 400 minus 40 minus 40 minus 1. So if you solve, you are going to get 45 mm. So it is too less, so if I am going to use, instead of 8 dia, I'll use 10 dia. So I'll get, spacing will be 70 mm. If I'm increasing the value, I'll get 100 for 12 dia legged bar. So anyhow, our minimum spacing we know 96 mm we have to provide. So 70 mm is less than 96 mm, so it is okay. So I'm going to use confining, for confining links, use two-legged 10 dia bar at rate of 70 mm center to center. Okay. So this nominal link is based on your shear capacity, because we have, our capacity is more. So I'm using the minimum tie bar area. Otherwise, you have to use this formula to calculate the spacing for nominal link. Okay, but we are providing the minimum. So for 8 dia bar, 200 mm center center. Then I have to calculate the confining length, which is 500 mm on either side of joint, and the reinforcement should be this spacing when I am assuming 10 dia bar. Okay, this confining link will continue. Okay, from the joint to both sides, 500 mm, 500 mm. Okay, in the next video, I will check the joint strength, whether it is because the concept of weak beam and strong column, we are going to check how the joint strength is there in the next video. Hope this video is useful for you. Thank you for watching.